taking a look at network problems. So in these situations, you have your diagrams to the right. It's going to break down and give us all the information that we need. So the following descriptions, and they're accompanied free body diagrams, show all the forces acting on the object in each. Calculate the work done by these forces. Use the format of force times displacement times cosine, FD cosine of theta, and calculate the total work done by all forces. So right now, work done by the normal force. So a 10 Newton force is applied to push a block across a frictionless surface for a displacement of 5 meters to the right. So I'm going to add in the fact that this thing is moving to the right. Now you may need to rotate this, but 0, 90, 180, 270, 360. These would be like degrees. Distance is going this way. So remember, it's how the force is and at what angle in comparison to displacement. So since this thing is moving to the right, any force that is in the same direction would have a cosine of 0. But look where normal force is. Normal force is being applied upward. So even though we have this thing moving to the right, the normal force is applying this upwards. So we're going to take the equation FD cosine theta. What is the work? All right, what is the force on the normal here? 20 newtons. Displacement is 5 meters. But at what angle? What angle would I pick? This thing's moving to the right. So if the force is going in the same direction, it would have a cosine of 0. Since normal force is going up, it would be 90 degrees. All right, so let's plug it in. FD cosine the angle. Get 0. Why? Because cosine of 90 is 0, and anything times that is 0. So no work is being done by the normal force. What about the applied force? The applied force is in what direction? Well, remember, this thing's moving to the right, so 0 degrees would also be then considered going to the right, and in which case we would have an angle of 0 degrees. We have 10 newtons of force, 5 meters worth of distance or displacement. Cosine of 0 is 1, so 5 times 10 is 50, times 1 is 50. You have positive 50 joules of work being done here. What about the last one? Well, it's the same force. Correct. It would be 270 in comparison. All right, if we look at our little chart here, and if you do 270 there instead of 90, okay, so 20 times 5 times cosine of 270, you're going to get 0 joules, and then you add them all up to find the total work done on the object, which is just going to be 50 joules. Okay, so now a 10 Newton friction force slows a moving block to a stop after it was moving a distance of 5 meters to the Right, so the displacement, guys, was to the right. So looking at this, normal force, all right, if it's going in this direction, we're going to consider that the 0 direction. That's where we replace our 0. If we said this thing was moving up, we would rotate the circle or rotate our little coordinate thingy to make sure 0 would always be in the direction of our displacement. So since it moves to the right, we're putting 0 to the right. Normal force would be going straight up, so that's 90 degrees. Gravitational force is going straight down, so that would be my 270 degrees. And friction force would be what? It would be 180. All right, and then plug in your numbers. So normal was 20 newtons, gravity was 20 newtons, friction force is 10. In each case, the displacement was 5 meters to the right. Multiply these out. So same thing, just like up top, cosine of 90 and 270 are both 0. So anything times 0 is 0. And like I had mentioned before, cosine of 0 itself is 1. The complete opposite would be negative 1. So 10 times 5 is 50 times negative 1. You're going to get negative 50. In adding all of those together, you get a total work done of negative 50 joules worth of work is done by the friction force. Still want my little coordinate plane showing here. Okay. What direction is the displacement of this thing, guys? To the right. It's important because that tells me what my directions are going to be. Distance, all right, or my displacement, direction. If it's to the right, we're going to make 0 going to the right. So that means the applied force will be what degrees? 0. Normal force, as it's pointing up, would be 90. Gravity is pointing down, which would be 270. And friction is going to the left, which would be my 180. It says 5 meters worth of displacement, so that's all my 5s here. Normal was 20, gravity was 20, applied was 10, and friction is 10. 90 and 270 are automatically 0. We've already done this calculation for my applied force in the first one, and that came out to be 50. And we did this one right in the problem above. This came out to be negative 50. And to find the total amount of work, you add everything up. So 0 plus 50 is 50, plus 0 is still 50, plus a negative 50. Total net work on this thing is 0. So when you're pushing something across at a constant speed like that, in this case, when we have everything wind up balancing out, you get a total work done on the object of 0. All right, and in this case, the last one here should be, rather simple. You have a 2 kilogram object, great. We don't need the mass in this case. It's being pushed across a frictionless surface to the right with a 5 meters of displacement. So the displacement is to the right. So that means going up would be 90. And going down is 270. Still 5 meters. 20 and 20. No work is being done on the objects. All right, so that's pretty simplistical there. You'll have time to look at those. These ones you can do. They're the same steps that we have just looked at. So okay, that's actually a good question. So in this case, tension and applied force are, all right, it's asking here now, it's a vertical displacement. So since D is going upward, you want to make sure whatever direction the distance or displacement is, we make that 0. So 0, and then you basically just kind of rotate it. 90, 180, and 270. So tension would be 0 degrees, and gravity would be 180. Okay, the vertical displacement is 5 and 5, 20 and 20. We just use these similar calculations up front, so you have 50 and negative 50, or a total of 0. Or you can... Hmm? Yep, you're right. Thank you. Yep, should be 100 and then negative 100. Thank you for catching that. And then this one, a dinner tray of plates is being held in the air and carried a distance of 5 meters to the right. So D will be going to the right. So you have your 90, 180, 270, and your 0. The applied force is going straight up, so that's at 90 degrees. The gravity or weight of this thing would be going down, in which case you're looking at 270 degrees. Because we're going the 5 meters to the right, and you're 20 and 20, cosine of 90 will be 0, and cosine of 270 will be 0, so 0 total work being done here. Okay, when a force is applied, number 9, when a force is applied to do work in an object, does the object always accelerate? No. No. All right, so some of the examples up there. Does the object always accelerate? No. If the net work on the object is 0, it's not going to accelerate, right? You can have some forces that balance and wind up preventing acceleration, so it's not always going to accelerate. Yes. Okay. So you can have forces that balance everything out, and in which case there will be no acceleration. And in the other cases, okay, you have work that balances out, positive and negative. So even though you do have work being done, the object is not always going to accelerate. Number 10, looking at the equation for work, FD cosine of theta. Chimney sweeper. You get it?
Yeah, that was not that funny.
It sounds like chimney sweeper. No, it's his name is Jim Knee Sweeper. like chimney sweeper, if you say it quick enough. Anyway, you have your equation. You're applying a 21.6 Newton force downward at an angle of 57.2 degrees with a horizontal to displace a broom a distance of 6.28 meters. So how I'm taking this is I'm applying a force downward. We'll just use the angle as is. And the force was 21.6 newtons. (57.2 degrees as my angle. And to move this sucker a distance of 6.28 meters. Okay, so we are looking at F of 21.6, distance or displacement of 6.28, and an angle of 57. Gotta be cosine of that. And I get 73.48 joules. Okay, then you have Ben. What's the last name? Ben Pumping Iron? No? So it seems like this guy's like been at the gym pumping iron. Bathroom, yes, go. So Ben applies an upward force to lift a 129 kilogram barbell to a height of this meters at a constant speed. Okay. So since it's at a constant speed, we know that this is mass. So we would need to know what Fg is. Fg is mass times gravity. So 129 times 10, which gives us 1,290 newtons. 1,290 newtons downward. The applied force is directly upward, and it's got to be the same if it's moving at a constant speed. So these two forces would have to be the same. So the applied force in this case will also be the 1,290. So that is the F for our equation. All right, so we have F 1290. How far does this thing move? We lift it to a height of 1.98 meters. Now, what about the angle? So if I'm pushing it up and the distance that this thing moves is up, if distance is going up and the force is in that direction, this would be 0, 270, I'm sorry, 180. And 270. And then in this case, since D is moving straight up, you're having a cosine value here of 0. So we're just going to type all that in. And you should come up with 2,500 and 2,554.2, and the unit for work, joules. Okay, now you got an elevator that has 12 occupants, and it's moving them up 21 floors, which is 76.8 meters up at a constant speed. So constant speed meaning, all right, the applied force that we're using here, or the tension force, has got to be equal to the weight. Okay, we'll just write applied force for now. It could be a tension force. We know that they have to be the same. Why? Because they're moving at a constant speed. There are 12 passengers. So remember, Fg, what is the equation for Fg? Okay, Fg, mass times gravity. It says the average mass of each person is 62.8 kilograms. Gravity, we're using 10. So the average person should weigh 628 newtons. But how many people are on there?
12.
There's 12. So we would need to multiply that by 12 to get the total weight. So what is 628 times 12? Cranking out 7,536 newtons as my overall weight. So that means the applied force also needs to be that. Distance is going, all right, our distance or displacement is going up, which means if that's going up, we want to make 0 degrees going up as well. Going down would be 180, but the elevator is moving these people up, all right? It's lifting them. So to find out the amount of work being done on this one, the force is the applied force, 7,536. The distance that this thing moves is a pretty large 76.8 meters. And we're doing this with a cosine of 0 degrees. So this times 76.8 times the cosine of 0. And we're kicking out an answer here of that's 578,764.8 joules of work. And that's how we do it. So that's essentially what we're going to be looking at, in a sense, tomorrow. Okay.